In this video, I'm going to discuss the concept of electronegativity, which is defined as the ability of an atom to attract a bonding pair of electrons. Now, this can be quite confusing for students because what do we really mean by the ability to attract a pair of electrons? Well, let's first think of an atom. This is the nucleus, which would have positive charges in it because it has protons, and then we have electrons around it. So if this atom was to attract a pair of electrons, it would be because this nucleus is able to exert a pull on these electrons. Now, this pull on these electrons will be determined by how strong the nucleus is and also how far away are these electrons from the nucleus and how much shielding is occurring because of the inner electrons. So pretty much the same factors that impact ionization energy will impact our electronegativity. So first up, the higher the nuclear charge, the higher the electronegativity if there is no change in distance or shielding effect. But if there is a change in distance, suppose it increases and the shielding effect increases, then the net effect of the nucleus on the pair of electrons that it's trying to draw toward itself will be less, and therefore the atom will have lower electronegativity. Now, this then sinks in with the next idea that how does electronegativity vary down the group and across the period. So in the periodic table on the left hand side we have what we call the metals, and in group 1 and group 2 we know them as elements that have low electronegativity or high electropositivity. Now compare these to the ones that are on the elements on the right hand side. They have high electronegativity. Why is that? Because as we go across a period from left to right, we are adding electrons to the same shell and we're making the nucleus stronger, but we're not increasing the distance and the shielding effect. As a result, the pair of electrons, as it approaches the atom, it will be attracted more strongly towards the nucleus as we go across a period. Now down the group, even though the nucleus is becoming stronger, the nuclear charge is increasing, but the distance from the nucleus of the electrons that are incoming will increase, and also the shielding effect would increase because there'll be more layers of electrons in the middle, so they'll repel the outer electrons, nullifying partially the force of the nucleus on the electrons. Now, as a result, down the group, electronegativity decreases, and up the group, it increases. So as we go up the group, it increases, and as we go across a period, it also increases. Now, if we exclude the noble gases from this equation, we have fluorine as the element that is on the top right corner of the periodic table, and that happens to be the most electronegative element in the periodic table. And then we have group 1 elements that are the least electronegative elements. Now this has important implications for how bonds will form between elements, and we'll get to that in a bit. Let's first go back to atoms and try to figure out what happens when atoms of the same electronegativity bond with each other, and when they have different electronegativities, what happens then when they try to bond with each other. So let's first take the case of an atom, which is represented by this red circle, and it's bonding with another atom that has the same level of electronegativity. And so we have a pair of electrons that we will call the bonding pair. So one electron has come from one and one from the other one, and this pair ends up being shared between two atoms. Why? because each of these has equal power to draw this pair of electrons towards itself. So what we have here is this atom is going to exert a pull on the shared pair, which is going to be the same in strength as the other atom. So in this particular case, we have the shared pair actually being spread out evenly between the two atoms, and we get a bond that is covalent in nature and is also non-polar. Why would it be non-polar? Because we have this region of negative charge spread evenly, so there is no one side that is more negative than the other. So there is no dipole on this molecule. Now, if we were to take elements of slightly different electronegativity, so let's take one that is more electronegative, represented in red. So here we go. And let's take another one which is slightly less electronegative and which is represented here in green. Now, if they have a pair of electrons to share between them, what will happen here is one of them will actually have a greater force of attraction exerted on these this pair of electrons compared to the other one, as a result of which the electrons here will still be shared, but there will be a distortion in the electron cloud. This shared pair, the cloud of this electron pair, will be more towards this element that is more electronegative, because this has more power to draw it in. Now, in this case also, the bond will be covalent, but we will have a bond which we call a polar bond. Now, that's because there is uneven distribution of negative charge. It's more towards the atom that is able to draw it in more, which is more electronegative than this one. So we end up having what we call a dipole on the molecule, and this will be represented by the symbol delta negative and delta positive. This meaning that there's a partial negative charge here and a partial positive charge here. Now, this is the case when there is a difference in electronegativity, but the difference is not so great. What happens if there is a very great difference in electronegativity? So that's represented here by these two atoms. One is red, which means that it's very electronegative. This is what I'm using it to symbolize that. And the other is something that's not very electronegative, so that's represented here in blue. Now, if I was to take a pair of electrons, a bonding pair of electrons between these two, and figure out how they are going to actually end up, we will find that the actual element, the atom actually that has very high electronegativity compared to the one that has low electronegativity, will pull the entire pair towards itself, so much so that it will end up producing two ions. It will completely snatch this pair of electrons towards itself to produce a negative ion, and this one will become a positive ion. And as a result, the bond formed will be ionic in nature. So here we have three different ideas. One where there is equal amounts of electronegativity. That means equal ability to attract a bonding pair of electrons. In that case, the sharing is even and the bond is non-polar covalent. If we have a difference, slight difference in electronegativity, then the bond is polar, and but it's still covalent because it's not an extreme case like this one where one atom has too much power compared to the other to draw in a bonding pair of electrons. Now, this actually has important implications for uh, how to how we can predict bonding will happen in the when we look at elements from the periodic table. So let's go back to our elements here. We have um, group 1, group 2, group 3 elements, metals. In O levels, a lot of people think that the metals and non-metals will always form bonds that are ionic. That's not always the case. So what happens in this particular case is that you have a very high electronegativity difference between elements that are on the left hand side of the periodic table and the ones that are on the right hand side. So for example, if I take sodium and chlorine and I pair them together, I end up getting an ionic bond, because the situation resembles a bit like this case here, where chlorine would be something that has a very, very high electronegativity compared to sodium. So it will snatch the pair towards itself and it will become negatively charged, and sodium will be a positively charged ion, and then we'll have an ionic bond forming. Now, what happens here is that if I get to something like aluminum, things become quite interesting, because aluminum, if I pair it with oxygen, the bond is still ionic. There's a high enough electronegativity difference, so it's like this arrangement here. But if I pair it with chlorine, the bond becomes covalent. And this is a situation that's pretty much like the one over here, because aluminum and chlorine have an electronegativity difference, but it's not high enough for the bond to become ionic. So the bond remains covalent, but it's a polar covalent bond. And then, of course, if I take any element, for example, bromine, and bond it with itself, then I will have two atoms that have equal power to draw electrons, because it's the same atom. So their electronegativities are the same. In this particular case, the bonding pair will be spread out evenly between the two atoms, and it will result in a covalent non-polar bond. So what we can predict is based on some known compounds. So for example, I know that aluminum oxide is ionic, and if I ask you what will be magnesium oxide, you know that if it's aluminum and oxygen have enough of an electronegativity difference for the bond to be ionic, then surely magnesium and oxygen will have a greater electronegativity difference. So their bond will also be ionic. We can, given certain information like this, we can predict the type of bonding between other elements. So here we are. This is the concept of electronegativity in a nutshell.